Hi students, the topic today we are going to see is about design of cooling tubes for a transformer. So for that we should know what is the modes of heat transfer in a transformer, modes of heat transfer. Okay, so we know that a power transformer carries high current, right? So when a transformer carries high current, definitely there will be a loss. Now this loss, majority of loss, it will be dissipated as heat loss. Okay, so the heat produced in a transformer has to be dissipated properly to the external environment in order to make the transformer to work efficiently. So as we all know, there are the methods of heat dissipation. We know there are three methods of heat dissipation, right? First one, it is conduction, convection and radiation. So these are all the three modes of heat transfer. Now how the in transformer, how these three way it is helping for dissipation of heat. If you see, if I consider a transformer, okay. So when a current is carried by the transformer, definitely the heat that is produced, we all know that the heat produced in the inner core of the transformer will be much higher compared to the external surface, right? So what will happen? Now the inner core heat will be dissipated on the outer surface of the transformer. Now this mode of heat transfer, we will call this as a conduction mode, right? Okay. Now from the outer frame of the transformer, the heat is, if in case suppose if it is immersed, if the transformer is immersed in the oil, the heat is absorbed by the oil, right? So then the heat will be reduced. So the oil will absorb the heat dissipated by the external surface of the transformer. Now this mode of heat transfer, it is called as convection. Okay. Now from the oil, the heat is absorbed by the air, or the heat in the oil, it is dissipated to the air. Now that is called as radiation. Now it has been observed that the heat dissipated by conduction is negligible in transformer compared to convection and radiation. And let us assume the ambient temperature as for a room temperature as 20 degrees Celsius. So the temperature rise, if we assume that as 40 degrees Celsius, so for 40 degrees Celsius, the transformer, if it is reaching temperature for 40 degrees Celsius, the heat dissipation by convection, right? It has been observed that the heat dissipation, the specific heat dissipation by convection, it is observed that it has 6.5 watt per meter square degrees Celsius. And the heat radiation, the heat dissipation by radiation, it has been observed as 6 watt per meter square degree Celsius, right? So now in order to maintain the temperature of a transformer at a particular level, the heat dissipation by conduction is negligible. The heat dissipated by convection I have mentioned here, and heat dissipation by radiation also I have mentioned here, right? Now let us see a plain wall tank, okay? That is, if I assume that this transformer is immersed in a plain wall tank, okay? It is immersed in a plain wall tank which is filled with an oil, okay? And if it is filled with the oil, definitely, as I said, by convection and radiation, the heat dissipation is more, right? So now if the surface area of the tank, if I assume that as S suffix T, let us represent the surface area of the tank as S suffix T, okay? So, in that case, the temperature rise of the transformer, okay, let us assume that as theta, and the heat, it is the heat produced in the transformer, it is due to the losses, right? So, what are all the losses that occurs in a transformer? One is iron loss, which is represented by Pi, and the other one is copper loss, right? Copper loss, which is represented by P suffix Cu, right? Okay. Now, the temperature rise of the transformer can be calculated using the formula theta is equal to total losses divided by specific heat dissipation into total area Okay. So, what are all the losses we have? Iron loss and copper loss. There are other there are other stray losses. We are neglecting it. We are considering only iron loss and copper loss, right? So, total loss is nothing but iron loss plus copper loss, Pi plus Pcu divided by specific heat dissipation. As I told you, the specific heat dissipation is due to convection and radiation, right? Okay. So, now we have to add, due to convection I told you it is 6.5 watt per meter square degree Celsius, and due to radiation it is 6 watt per meter square degree Celsius. So, you have to add this. So, you will get 6 plus 6.5, okay, which is nothing but 12.5. Am I right? 12.5 into total area. What is the area of the tank? That is nothing but S suffix T. So, now the temperature rise of a transformer can be expressed as Pi plus Pcu divided by 12.5 into S suffix T. Okay. So, this is what the temperature rise in a transformer for plain walled tank. When the transformer is immersed in the tank which is filled with an oil, the temperature rise of the oil or the in the transformer we can calculate with the help of this formula theta is equal to Pi plus Pcu divided by St, 12.5 into St. Okay. So, now if the power rating of the transformer is huge, then definitely the loss will be huge, right? In order to dissipate the heat, what we have to do, this heat loss, either we have to increase the size of the tank, right, in order to increase the volume of the oil. Okay. Now, there will be a space constraint, right? In that particular section where the space constraint is there, or for in order to have an economical reason, what we are trying to do is, okay, we will have the same tank area, but we are going to provide a cooling tube. Okay. We are going to provide the cooling tubes on the surface of the transformer. Okay. Now, this cooling tube, what will happen is, it will give a provision for the oil to circulate. And not only that, when cooling tube is there, okay, so this cooling tube will also, it will also give some space for the oil, right? So, the area, the volume of the oil will increase if more cooling tubes are placed on the surface of the tank. So, if cooling tubes are placed, how the temperature rise is going to relate, and how the temperature rise is maintained or reduced with the help of cooling tube, we are going to see in the next section. So, next is design of cooling tubes. So, the purpose of designing cooling tubes is, as I told, the heat dissipation by convection will be higher compared to radiation, okay, and conduction. Conduction we are neglecting it. Now, if I provide a cooling tube on the surface of the tank, transformer tank, it will increase the heat dissipation by convection method, right. So, let us see how these cooling tubes are calculated. What is the formula to calculate the number of cooling tube that is required for a given transformer. Okay. So, we have already seen for the plain wall tank, the formula is theta, temperature rise theta is equal to Pi plus Pc divided by 12.5 into St. Now, when a transformer is given, is a transformer tank, when cooling tubes are added, definitely it is going to occupy some portion of the cooling tube, the tank surface, isn't it? So, tank surface, what we have assumed, that is St, right? The area of the tank we have assumed as S suffix T, right? So, this cooling tube, it will occupy X portion of the wall of the tank, right. So, what is St? St is nothing but area of the tank, is St, okay, and area of covered, the total area covered by area of cooling tubes. Area of cooling tubes. What is that? That is nothing but X into St. Now, what is X? X is nothing but the portion of the surface area of the tank. Okay? It is the fraction of the surface area of the tank. The fraction of the surface area of the tank. Okay. So, now what is the total area? Total area. The total area of the tank now it will become total area of the tank. Okay. Now it will become as St is tank area plus X into St, right, plus X into S suffix T. So, I can write this as S suffix T 1 plus X, right, S suffix T 1 plus X. Consider this as equation 1. Now, by providing cooling tubes, as I told, the convection the heat dissipation by convection, it is going to increase. Let us assume that the heat dissipation is improved by 35 to 40 percentage. Now, let us assume that as 35 percentage it has been improved. Okay. So, what is heat dissipation by convection? I have earlier mentioned it as heat dissipation by convection, heat dissipation, specific heat dissipation, okay, specific heat dissipation by conduction, specific heat dissipation by convection, it is 6.5, right, into already 6.5 watt per meter square degree Celsius, it is dissipated by plain wall tank, right. Now, along with that, by adding cooling tubes, right, by convection, by adding cooling tubes, that will be 35 percentage I told you. So, in that case, it will be 135 divided by 100. Okay. So, loss dissipation. So, 6.5 into 135 divided by 100, right. So, now that will be around 8.8 if I am right. Okay. It is around 8.8. So, now the heat dissipation, it has been improved by 35 percentage, means It is 8.8. In case if I am considering this as 40%, then it will be 140 divided by 100, which will be equal to around 9.1. Okay. So now, ஸ்டாப் பண்ணலாமா? அது அப்புறமா இது பண்ணிக்கிறேன், ஒரே நிமிஷம் செக் பண்ணிக்கிறேன். Now we are going to consider only 35% means specific heat loss we have calculated. Okay. Now we will calculate loss dissipated. Loss dissipated. So loss dissipated, how will you calculate? Specific heat, if I know, loss dissipated by the tank. How will you calculate? It is nothing but by the tank, by providing tubes. By providing or by the tubes, first we will calculate. Loss dissipated by providing tubes. Okay. By providing tubes means specific heat is 8.8 into area. What is the area of the cooling tubes? It is X into S suffix T. Okay, so loss dissipated by providing tube is nothing but 8.8 into X into S suffix T. Okay, and loss dissipated by plain wall tank. By plain wall tank already we have calculated, right? Already we have calculated by plain wall tank. By plain wall tank, it is nothing but 12.5 into S suffix T. So the total loss dissipation, by of a tank by providing cooling tubes, will be equal to plain wall tank is 12.5 S suffix T plus by providing cooling tube the heat is improved by 8.8 into X suffix T, dissipation is added, right. So, it is 12.5 S suffix T plus 8.8 X into ST, right. So, ST you can take commonly outside. So, ST 12.5 plus 8.8 X, right. Okay. So, you can consider this as, already I have given one equation, no? You consider the total area, right. The total area already we have numbered that as the total area of the tank including tube as S suffix T 1 plus X, right. And this is the total loss dissipated of a tank by providing cooling tubes will be equal to S suffix T in bracket 12.5 plus 8.8 into X. Consider this as equation 2, right. So, now can you calculate this specific heat dissipation? You can easily calculate, alright, because we have calculated total area and total loss dissipated. Now, we know the specific heat loss dissipated by convection and radiation. Okay. What is that? That is nothing but loss dissipated per meter square. Am I right? Per meter square, which is equal to, the formula is total heat loss divided by total area. So, from equation 1 and 2, you will get what is total heat loss? Total heat loss is S suffix T in bracket 12.5 plus 8.8x. So, S suffix T, so equation 2 plus 8.8x divided by total area is equation 1, right? Okay, so from 1 and 2, we will get specific loss or loss dissipated per meter square by convection and radiation. So, total area is S suffix T 1 plus x. So, specific heat loss will be equal to 12.5 plus 8.8x divided by 1 plus x. So, this expression 3 will give you the specific heat loss dissipated per meter square due to convection and radiation. Okay, next what we have to calculate? We have to calculate theta, temperature rise. What is the temperature rise? What is the expression of the temperature rise? By providing cooling tubes, that we have to calculate it, right? So, for that, what is the formula to calculate temperature rise? Temperature rise formula is total loss. So, temperature rise formula, this is for plain wall tank. So, by providing cooling tube, temperature rise theta can be calculated as, the formula is total loss Pi plus PCU divided by total loss dissipated. What is total loss dissipated? Total loss dissipated is equation 2, right? So, S suffix T 12.5 plus 8.8 into x. Okay, this is the formula. Consider this as equation 4. Now, this is the formula. Equation 4 will give you the value of temperature rise when cooling tubes are provided on the surface of the tank. I think from this expression, it is easy for us to calculate the x area, right? So, let us try to calculate that area occupied by the cooling tube. Okay. So, we are going to find the value of x now. So, for that, let us just interchange the denominator. Okay. So, the expression, this expression I am taking. So, you can take this 12.5 plus 8.8x on the other side, on the left hand side, and in the right hand side I can consider Pi plus PCU divided by theta into S suffix T, right? Okay. So, from equation 4, we got this one. So, this again can be written as Pi plus PCU divided by theta into ST. This 12.5, let me bring on the other side. So, it will be minus 12.5. So, 8.8x equal to Pi plus PCU divided by theta ST minus 12.5. So, what is x now? X will be equal to 1 divided by 8.8 in bracket Pi plus PCU divided by theta S suffix T minus 12.5. Consider this as equation 5. So, equation 5 will give you the formula to calculate the portion or the area occupied, the total area occupied by cooling tubes, total area occupied by cooling tubes. X is equal to 1 divided by 8.8. Okay, now Since how you got this 8.8? By considering that the heat dissipation is improved by 35% by providing cooling tubes. Suppose if it is 40%, then this 8.8 will become 9.1, which we have seen already. Okay. So, here we have assumed that 35% of heat dissipation is improved by providing cooling tube. That is why we are getting this as 8.8 in the denominator. We are getting this as 8.8, or otherwise 40% means 9.1. So, based upon the heat improvement, how many percentage we are considering, based upon that you just multiply that with that convection 6.5 that value. So, you will get this number. Okay. So, by this is the, what is X now? Total area occupied by the cooling tubes. Okay. Now, the next question will be, we have calculated the value of area occupied by cooling tubes. Now, how many number of cooling tubes that we have to place around the surface of the tank? So, that we have to calculate. Our next step is to calculate number of cooling tubes that has to be provided around the surface of the tank. So, that we have to calculate, isn't it? So, for that the formula is, if I know the total area of the occupied by the tubes and area of one tube, then what is the formula? How will you calculate NT? Total area occupied by the tubes. Total area occupied by tubes, which we have calculated, which already it is there, equation 5. Total area occupied by tubes divided by area of one tube, area of one tube, right? So, this is the expression to calculate number of cooling tubes. Total area occupied by tube is this equation 5. Area of one tube we have to calculate. So, for that, let us consider that. So, if I consider this as tube, okay, one cooling tube, consider the diameter of the cooling tube as d suffix t. Diameter of the cooling tube as d suffix t, and the length of the cooling tube. The length of the cooling tube as L suffix t. Diameter of the cooling tube as d suffix t, length of the cooling tube as Lt. Now, how will you calculate the surface area of this cooling tube? It is nothing but surface area of a cylinder, right? So, area of one tube will be nothing but area of one tube, formula pi dt Lt, surface area, right? Pi, we know that is nothing but pi dt 2 pi RH, right? So, pi d suffix t dt Lt. So, now let us try to substitute here. Total area of the tube is nothing but 1 divided by 8.8 in bracket Pi plus Pc divided by 12.5 plus, sorry, theta st, sorry. So, let us write here. So, area of one tube. So, total area of occupied by 1 divided by 8.8 Pi plus Pc divided by theta into S suffix t minus 12.5. Area of one tube is nothing but pi into dt Lt. So, consider this as equation 6. Yes. Now, the number of cooling tubes that has to be provided for a given transformer tank can be expressed as NT equal to 1 divided by 8.8 into pi dt Lt in bracket Pi plus Pc divided by theta into St minus 12.5, right? Okay. Now, in case if in the problem, okay, the designer, I mean in the problem, if they have not given the value of diameter of the tube or length of the tube, you can consider the diameter of the tube as 50 mm. Also, the length of the tube, if it is not given, you can consider that as 1 meter. 50 mm dt, diameter of the tube, and length of the tube as 1 meter, you can consider if it is not given in the problem. Okay. So, I hope like you can understand how the number of tubes in a cooling tube is calculated, and we have seen what is the necessary for a tank, a cooling tank for a transformer. Huge power heat loss will be there. So, there is a we need a oil filled tank. And I forgot to mention one thing, there are different methods of cooling, which is a separate chapter, cooling methods of transformer. So, basically it can be categorized as natural cooling and forced cooling. Okay. The method by providing cooling tubes, what I have explained you is about you can have a fan. In that case, it is forced oil cooling. Okay. So, air cooling it's there, okay, and forced air cooling, oil cooling. Okay. So, the different types of cooling methods there, that is different section. Now, here we have what we have seen in this section is how to calculate the number of cooling tubes for a given transformer. So, that we have calculated it, right. Okay. Now, in case in the problem, to solve the problem, if they have given the dimension of the transformer, okay, how to calculate? Assume that they have given the dimension of the transformer tank. What are all the dimensions if they have given? Assume that, so here the transformer is immersed, okay. Consider the transformer is immersed in a tank. Consider this as width of the transformer, Wt. Let us make it as W suffix T, because small t is for cooling tube. No, this is tank. So, let us consider that as width of the tank. Okay. So, transformer immersed in a cooling tank. Consider this as width of the tank, okay, and this as length of the tank, and let H suffix T be the height of the tank, height of the tank, okay. So, now how will you calculate the surface area of the tank, S suffix T, okay. So, S suffix T, surface area, means the heat cannot be dissipated at the bottom of the tank, and at the top of the tank you have leads, conservator, right, bushings, everything it is will be there. So, the heat transfer on the top of the tank, it is not possible, only on the vertical sides the heat will be transferred, right. So, how will you calculate this area? This area, how will you calculate? It is nothing but a square, rectangle, right, or a square. If you assume, I can multiply Wt into Ht, right, Wt into Ht, Wt into Ht, right. We have other side also. So, this side and the other side. So, it is 2 Wt into Ht. Similarly, how will you calculate this portion? Lt into Ht. On the other side, so it is 2 Lt into Ht. So, 2 you can take commonly outside, Ht you can take commonly outside. So, the formula is 2 Ht 2HT in bracket LT plus WT. This is the formula to calculate. If the dimension of the tank is given, to calculate surface area of the tank, the formula is 2 into HT in bracket LT plus WT. Okay. Suppose if they have given only the transformer dimension if they have given, then how to calculate HT, WT and LT, let us see. The formula is, if the transformer dimension is given, okay. So, if I try to view the top view of the transformer, if it is a single phase transformer, the top view of the transformer, top view of the transformer, I can see like this, right? This is what I can see, right? And the windings, the transformer frame and the windings. Okay, this is top view and this is cross sectional view. Assume the diameter of this winding as d suffix e, d suffix c, and center to center distance, already we have represented that as capital D. Okay. Now, first let us try to calculate the width of the transformer. In order to calculate the width of the transformer, okay, calculate the width of the transformer means this is width of the transformer, am I right? Width of the transformer, okay, width of the transformer, you have to add D, right, this T. Then half DE plus half DE, so it is DE, okay. So, D plus this portion, half DE plus half DE, right, that will become DE. Consider this clearance. There will be some clearance between the wall of the tank and the transformer winding, right? We have to give some clearance, and this clearance will increase if the volume of the oil is, if the power rating is higher, if the voltage rating is higher, this clearance will increase. So, based upon the voltage and current rating, the clearance accordingly we have to give. Okay. So, let us assume that the clearance as C1. So, then that will become 2C1. So, width of the transformer is nothing but distance between the two limb capital D plus external diameter of the winding plus 2C1. This is for single phase transformer. In case if it is a 3-phase transformer, obviously then we will have one more transformer frame and winding. So, D you will have 2D, right? All the other thing it remains same. Okay. So, 2D plus DE plus 2C1 for 3-phase transformer, width of the transformer. Okay. Next, we have to calculate length of the transformer, right? Length of the transformer L suffix T. L suffix T. Obviously, this clearance we have to give. Consider this clearance as C2. So, how will you calculate length? This we know, what is this value? D suffix C. So, the length of the transformer will be equal to D suffix C plus C2, 2C2. Whether it may be single phase transformer or 3-phase transformer, this remains same, right? The length, it is not going to increase. Only the width of the transformer it will increase when it is a 3-phase transformer. So, the length of the transformer for single phase or 3-phase, it remains same. Single phase and 3-phase, the formula remains same. Okay. Next, we have to calculate height of the tank, HT. Height of the tank, HT. Suppose, if the height of the transformer frame, if they have given as, already we know height of the transformer frame, it should be represented as H. Okay. So, if H we know, then at the top portion and at the bottom portion we are giving some clearance. Consider from the bottom of the tank to transformer frame, C3 is the clearance, and from the top of the transformer to transformer top, C4 as the clearance. Okay. So now HT will be equal to formula H plus C3 plus C4. So height of the tank will be equal to H plus C3 plus C4. Even HT will remain same whether it is single phase or three phase. Okay, whether it is single phase or three phase, it remains same. So now let us try to recollect all the formulas, whatever we have seen in designing the cooling tubes. Okay. So first we have calculated the number of cooling tubes. What is the formula? Number of cooling tubes NT equal to 1 divided by 8.8 pi dt LT in bracket Pi plus PC divided by theta S suffix T minus 12.5. This is number of formula to calculate number of cooling tubes, right? Next, if surface area, if the tank dimensions are given, how will you calculate surface area of the tank? Surface area of the tank is equal to 2 into HT in bracket LT plus WT. Next, if transformer dimension is given, then how will you calculate width of the tank, length of the tank and height of the tank? First, let us calculate width of the tank, which is equal to D plus DE plus 2C1 for single phase, and for three phase it is 2D plus DE plus 2C1. And length of the tank DE plus 2C2 for both single phase and three phase. And similarly, next, height of the tank, H is the height of the transformer frame, plus C3 clearance from the bottom to transformer frame, plus C4 clearance between top of the transformer frame and top of the transformer tank. So these are all the formula which we have to keep in mind in order to solve a problem in designing of cooling tubes. Hope you would have understood clearly about how to design a cooling tube. Okay. Next, we will try to solve a problem in this. So last section we saw how to calculate the number of cooling tubes in a transformer, right? So let us see now how to solve a given problem and how to estimate the number of cooling tubes and how to distribute that around the surface of the tank wall. Okay, so let us consider a problem. 1000 kVA, 6600/440 volts, 50 hertz, delta to star connected core type 3-phase transformer, where the adjacent limb distance between adjacent limb they have given as 0.47 meter. External diameter it has been given as 0.44 meter. Diameter of the winding, external diameter of the winding, D suffix C, right? It is 0.44 meter. Height of the transformer frame is given as 1.24 meter. Iron loss Pi they have given as 3.7 kilowatts. Copper loss 10.5 kilowatts. Temperature has to be maintained at 35 degrees Celsius. Diameter of the tube as 50 mm. Length of the tube they have given in the problem itself as 1.05 meter. In case if it is not given, I told you in the last section, it has to be considered as 1 meter. And heat dissipation, it is improved by providing cooling tube due to convection as 35% we are assuming it. So in that case, now they are asking us in this problem, we have to design a tank with cooling tubes. Let us try to calculate the number of cooling tubes for a given transformer and how to place that around the surface of the transformer. So the formula, number of cooling tubes is equal to N suffix T equal to 8.8 pi into dt LT in bracket Pi plus PCU divided by theta into S suffix t minus 12.5. So, this is the formula, right, to calculate number of cooling tubes. So, let us try to calculate number of cooling tubes. 1 divided by, how we are getting 8.8, because we have considered 35% heat dissipation is improved by cooling tubes due to convection. In case if it is 40%, then this 8.8 will become 9.1 into pi into diameter of the cooling tube. They have given us dt, they have given us 50 mm. So, you have to convert that into meter. 50 into 10 to the power of minus 3 into length of the tube is 1.05 meter, and in bracket, okay, 14.1 kilowatts divided by temperature is 35 degree into surface area of the tank. We have to calculate, right, surface area of the tank. We have to calculate. So, let us calculate surface area of the tank first. Okay. So, we will keep this ST as it is. Okay. So, now we have to calculate surface area of the tank. What is the formula to calculate surface area of the tank? ST equal to, yes, come on, 2 into HT in bracket LT plus WT. Am I right? So, now let us try to calculate the height of the tank. What is the formula to calculate height of the tank? Instead, we will calculate first width of the tank. Width of the tank. Since it is a 3-phase transformer, width of the tank is 2D plus DE plus 2C1. Since they have not given the value of clearance, we will assume value of clearances as different clearance is there, no? So, C1 we will assume 70 mm. C2 we assume 90 mm up to 1000 kVA rating. C1 clearance 500 to 1000, C1 70 mm, C2 90 mm, C3 50 mm from the bottom, and C4 300 mm. See, then you will have to give some clearance for leads, okay. That is also we will consider around 300 mm. So, WT equal to 2D plus DE plus 2C1. You substituted 2 into, what is the value of D? Capital D, it is 0.47, right? 0.47, external diameter, it is external diameter 0.44. 0.44 plus 2 into clearance, I told you the clearance is 70, but it is in mm, you have to convert that into meter, 70 into 10 to the power minus 3. So, width of the tank you should get as 1.62 meter. Okay. Similarly, you try to calculate length of the tank. Formula I told you already, D suffix C plus 2C2. So, substitute the value of D suffix C and the clearance, you will get around 0.62 meter. Okay. Similarly, you try to calculate H suffix T, height of the tank. Okay. What is the formula to calculate height of the tank? H plus C3 plus C4 plus clearance for leads. Okay. So, if I substitute the values of H, C3, C4, height of the tank, I should get around 1.9 meter. Now, you should keep in mind always the height of the tank should be greater than length of the tube. Height of the tank should be always greater than length of the tube. So, we have calculated now all the dimensions of the tank, okay, where only transformer dimension is given. From that we have calculated the dimension of the tank. Next we will try to calculate the surface area of the tank, substitute all the values. So, finally you should get ST value as 8.13 meter square. You try to substitute the values, you will get around 8.13 meter square. Okay, now in order to calculate the number of cooling tubes, substitute this value as 8.13, ST value as 8.13. Okay. Now, after substituting it, this is in kilowatt, convert into watt. Okay. So, finally, you will get, okay, you have to convert this into watt. Finally, you will get around 154 tubes. Okay. Around 154 tubes we have to place around the frame of the transformer tank, around the wall of the transformer tank. Okay. So, now that part is very, very interesting because it is just playing with cooling tubes. Okay. we are going to see how to place this cooling tube around the surface of the wall. So, let us draw the top view of the tank. Okay. So, width of the tank you should, what is the width of the tank? It is once convert into mm. So, it will be 1620 mm, right. And what is the length of the tank? It is 0.62 if I am right. So, you convert that again into mm, it is 620 mm. Now, always how we have given clearance for transformer and tank. Similarly, when you are providing cooling tubes around the surface, we have to give a corner clearance for the transformer tank. Corner clearance we have to give. That clearance, it is around 50 mm. Okay, 50 mm we should give at each corner. We have to give some clearance, that is 50 mm. So, what is the net length for which I have to place the cooling tube? Along with, now it will be reduced to 1520 mm, right. I think this is 1.52 u watt. So, it is 1.1420 mm, and this will be 520 mm. Now, we are going to place how many cooling tubes it is required along the width. So, along width, similarly along length, how many cooling tubes we have to keep, we are going to estimate. So, first row, along width, first row how to calculate? For that, we know the diameter of the cooling tube is 50 mm and the distance between two cooling tubes, okay, it is always 75 mm. You should keep in mind that the distance between two cooling tube, it should be always 75 mm, that clear, center to center distance. It is not distance between. Center to center distance of cooling tube, it should be 75 mm. So, in that case, the net length is 1420 divided by clearance. If you give, okay, it will come around 18 tubes along with in this side. Similarly, we have on the other side, we have to keep this 18 tubes, no? So, totally first row along with we will have 36 tubes. So, what is the remaining tube? How many remaining tube now we will have in the first row after placing all the cooling tubes? 18 plus 8 is 18 is 36. Total tube is 154 minus 36. Okay, it is around 128 tubes it will be remaining now. So, how to place these tubes? First row you place so on all the tubes along length 18 tubes and here also so on first row 18 tubes. Okay. Now, along length we have to calculate. Along length it is 0.62 and 100 clearance we have given. So, it is 520 divided by 75, you will get around 7 tubes. So, first row on both side we will have 7 plus 7, 14 tubes. 14 tubes. So, what is the remaining tube in the first row along length? 128 was the remaining tube along with. Now, here 128 minus 14. So, it will be 114 tubes will be remaining. Okay. If you place the tubes whatever we got along length and along width. So, along length we have to place 7 tubes, isn't it? And similarly here also 7 tubes. Okay, so you can mark this as 7 and here also 7. So, next this 115 tubes where we have to keep? In the next row. Okay, so for that no need to do all this the calculation and all. Directly first row it had 18 tubes, isn't it? In the second row reduce 1 tube. So, you will have in the second row along with in the second row first it was 18, now it will be 17 tubes. Okay, 17 tubes on both sides. So, 17 plus 17 it is 34 tubes. It is 34 tubes. What is our remaining tube? It is 114 tubes, isn't it? Okay. So, remaining tubes along length in first row it is 114. So, what I have to do now? 114 minus 34 tubes I have to do. So, we will get around 80 tubes, isn't it? Remaining will be 80 tubes will be remaining. So, how to place this? So, in between gap it is there, no? First row, between two tubes you have to place this 17 tubes along length. Like that, 17 tubes we are supposed to place. Okay. Similarly, along length, first row it had 7 tubes, no? Now you have to place 6 tubes. Okay, you have to place 6 tubes. Similarly, here also 6 tubes. So, here it was only 80 tubes, second row. Similarly, along length, second row, how will you calculate? Just you are subtracting 1. So, 6 plus 6, 12 tubes. So, at the end of second row, okay, after placing the tubes in the second row on all these sides, the remaining tube, how much you will have? Remaining tube, 80 tubes, 80 minus 12, right? Around 68 tubes will be pending. Around 68 tubes will be pending. Now, I think it is much easier for you to calculate for other rows, right? For third row, how will you calculate? Reduce 1, 17, you reduce 1, then it will become 16 plus 16, right? So, third row will have 16 plus 6, 16, 32 will have. So, what is the remaining tube at the end of second row? 68. So, 68 minus 32. Okay. So, how much you will have? You will have remaining 36 tubes, isn't it? Along the third row. So, place like this along the length. Okay. 16. Now, along length, third row, along length how much? 6, second row. So, next it will be 5, right? So, 5 plus 5, 10 tubes, 10 tubes. Okay. So, at the end of third row, placing the tubes around the third row of surface, okay, you will get 36 tubes minus 10, right? 36 minus 10, 36 minus 10. So, the remaining will be 26. 26 tubes you will get, remaining tubes it is only 26. Now, next what we have to do? This 26 tubes we have to place along the width. Along the width, fourth row we have to form then. Fourth row how much it will be? It will be 15 plus 15, which is equal to 30 tubes. 26 tubes is remaining, we can place 30 tubes also. So, you can increase the tubes, okay, increasing 4 tubes, it won't make much difference. In case by increasing the number of cooling tube, the heat dissipation is going to increase more only, which will increase the efficiency of the system. Okay. So, I have placed 15 tubes. So, totally if I add all the tubes, no, it will come around 154 tubes or up to 160 tubes you can go. So, this is how we are supposed to solve a cooling tube problem. Hope you would have understood. Thank you.